Good morning, one and all. Welcome in Sanjeevanee Mahavidyalaya Chapoli. This lecture is for B.Sc Physics TY students, paper number 13A, Bonding in Solids and X-ray Diffraction, lecture number 4. In last lecture, we have seen hydrogen bonding, importance of hydrogen bonding in our day-to-day life. Today we discuss about the diffraction of X-rays and Bragg's law. What is Bragg's law? What is its statement? How Bragg's law is helpful for study of crystals in solid. What is its mathematical expression? These things I want to tell you in this lecture. Now let's turn to Bragg's law. Bragg's law gives the angle for coherent and incoherent scattering from a crystal lattice. See, whenever X-rays are incident on an atom, they make the electronic cloud move as does any electromagnetic wave. The movement of these charges radiates waves with the same frequency. This phenomena is known as Rayleigh scattering, or we say elastic scattering. Once more I will tell you, whenever X-rays are incident on an atom, these X-rays cause to make the electronic cloud move as does any electromagnetic wave. And because of the movement of these charges, radiates waves with the same frequency. I mean, waves radiated by the moment of the charges has the same frequency as that of the electric charges. This phenomena is called as Rayleigh scattering. It is also known as elastic scattering. You see now here picture. Here X-rays. You see X-rays in phase, here in phase, and D is nothing but what? This is the distance between two layers of a solid crystal, small d. Here d it is shown. Here d sine theta, d sine theta. In this way, this is the effect of X-rays. Whenever we allow to pass X-rays, incident X-rays on the solids. Then a similar process occurs upon scattering neutron waves from the nucleus. These re-emitted wave fields interfere with each other either constructively or destructively, producing a diffraction pattern on a detector or film. It produces a diffraction pattern on the film. The resulting wave interference pattern is the basis of diffraction analysis. This analysis is called as Bragg diffraction. See now experiment. This is the X-ray tube. X-rays are produced here. These X-rays are allowed to fall on the crystal through collimators. Here it is a filter used, I mean matching filter is used in this experiment. And there is a single crystal here. On this crystal, X-rays are allowed to incident, and these X-rays, because of the presence of the crystal, instead of moving in this direction, in straight forward direction, they deflect, diffraction, and they are forming an angle of 2 theta. And here a detector is utilized, which detects the nature, structure of the crystal here. In this way, by using collimator and detector, X-ray tubes, matching filters, we can it can be used in Bragg's laws, and detector is used to detect the structure of the crystal. Bragg's diffraction, also referred as the Bragg's formulation of X-ray diffraction. Bragg's diffraction was first proposed by William Lawrence Bragg and William Henry Bragg in 1913 in response to their discovery that crystalline produce surprising patterns of reflected X-rays. The concept of Bragg diffraction applies equally to neutron diffraction and electron diffraction processes. See, in 1913, first proposed that the crystal has surprising pattern and it can be studied by using the reflected X-rays. And the crystal has very surprising pattern of arrays depending upon nature of the cells, unit cells utilized in the crystals. W.L. Bragg explained this result by modeling the crystal as a set of discrete parallel planes separated by a constant parameter d. This d is nothing but distance between two layers of the crystal, small d. It was proposed that incident X-ray radiation would produce Bragg peak if their reflections of the various planes interfered constructively. The interference is constructive when the phase shift is of multiple of 2 pi. Whenever there is a phase shift of 2 pi, multiple of 2 pi, interference pattern will exist. See here now, X-ray beams are there given. 1, 2, 3, such a various layers of crystals are there. Distance between these two crystals is taken as small d. Here you see in this figure, this is a solid, only two layers are shown here, plane, this is the plane view, front view, or only a diagrammatic view of X-rays diffraction. The X-rays having wavelength lambda, they are obliquely incident on the crystal structure or on the crystal. Suppose this is first ray, this one is second ray, both are parallel to each other. These are the X-rays having wavelength lambda. They are parallel to each other. They are incident obliquely on the crystal structure or on the crystal. One ray is incident at G, other X-ray is incident at O. Here this angle formed is what? Theta. Here alternate angle, this angle is also what? Theta. Alternate angles are congruent as these layers are parallel to each other. The ray which is incident at G is going to reflect along this direction. The ray which is incident at O is going to reflect in this direction. And here angle is obliquely incident, that is theta, and then this angle is also what? Theta. Now let's draw OF perpendicular to this incident ray and OH perpendicular to this incident ray. These yellow marks shows that OF is perpendicular to incident ray this, and another yellow mark is shown here. It is perpendicular to this ray, this refracted ray. This is about the incident ray, refracted ray, formation of angles, and so on. Now let us see the relation. Bragg explained this result by modeling the crystal as a set of discrete parallel planes separated by constant parameter d, we have shown in figure. It was proposed that the incident ray X-ray radiation would produce Bragg's peak if the reflections of the various planes interfered constructively. The interference is constructive when the phase shift is multiple of 2 pi. So Bragg's law given as n into lambda is equal to 2d sin theta, where n is an integer, lambda is the wavelength of incident waves, and d is nothing but what? D is the space or distance between the two planes of the atomic lattice, and theta is the angle between incident ray and the scattering plane, which already I have shown you in figure. Bragg's law derived by physicist William Lawrence Bragg in 1912 and first presented on 11th November 1912 to the Cambridge Philosophical Society. Although simple, Bragg's law confirmed the existence of real particles at the atomic scale, as well as providing a powerful new tool for studying crystals in the form of X-ray and neutron diffraction. So William Lawrence Bragg and his father Sir William Henry Bragg were awarded the Nobel Prize in physics in 1915 for their work in determining crystal structures beginning with sodium chloride and zinc sulfide as well as diamond. So in this way, Bragg's diffraction occurs when electromagnetic radiation or subatomic particle waves with wavelength comparable to atomic spacings are incident upon a crystalline sample are scattered in a specular fashion by the atoms in the system and undergo constructive interference in accordance to Bragg's law. For a crystalline solid, the waves are scattered from lattice planes separated by the interplanar distance d, where the scattered waves interfere constructively. They remain in phase since the path length of each wave is equal to an integer multiple of the wavelength. The path difference between two waves undergoing constructive interferences is given by 2d sin theta, where theta is already the scattering angle. This leads to Bragg's law, which describes the condition for constructive interference from successive crystallographic planes. So in this way, Bragg's law gives us the relation that is n into lambda is equal to 2d sin theta, where d is the interplanar distance, distance between two planes of a crystal, and theta is nothing but the angle between the incident X-ray and the plane, plane of the crystals. So in this way, Bragg's law is useful for the study of crystal, for the study of crystal structure. Then X-ray diffraction, Law's method, and rotating method we discuss